Lesson: Bayesian networks for decision making. Bayesian networks are powerful tools for decision making, offering a probabilistic graphical model framework that facilitates reasoning under uncertainty. These networks leverage Bayes' theorem to update the probability of a hypothesis as more evidence becomes available. In decision-making contexts, BNs provide a structured way to represent and analyze the dependencies among different variables, helping professionals make informed decisions even when data is incomplete or uncertain. At the core of Bayesian networks is the representation of variables as nodes and the dependencies between them as directed edges. This graphical representation makes it easier to visualize complex relationships and understand how changes in one part of the network can impact the whole system. The power of BNs comes from their ability to model causal relationships, allowing for the computation of the likelihood of various outcomes given specific actions or events. This makes them particularly useful in fields like healthcare, finance, and engineering, where decision-making under uncertainty is common. One of the practical tools for implementing Bayesian networks is the software package Netica, which provides a user-friendly interface for creating and analyzing BNs. Netica allows users to input data, define relationships, and compute posterior probabilities efficiently. For instance, in healthcare, a BN might be used to model the progression of a disease, taking into account various risk factors such as age, lifestyle, and genetic predispositions. By updating the network with patient data, healthcare professionals can predict outcomes such as disease progression or response to treatment, enabling personalized care strategies. To illustrate the practical application of Bayesian networks, consider a case study from the automotive industry. A manufacturer might use a BN to model the reliability of a vehicle component, incorporating variables such as material quality, manufacturing process, and usage conditions. By analyzing the network, the manufacturer can identify the most critical factors affecting reliability and prioritize improvements. This approach has been shown to reduce warranty costs and enhance customer satisfaction by ensuring that resources are allocated to address the most impactful issues. A key advantage of Bayesian networks is their ability to incorporate expert knowledge alongside empirical data. This feature is particularly valuable in domains where historical data is scarce or where new phenomena are emerging. Experts can define the structure of the network and assign initial probabilities, which can then be updated as more data becomes available. This iterative process allows for continuous refinement of the model, ensuring that decision-making is based on the most current and relevant information. In addition to Netica, another practical tool for working with Bayesian networks is the R package BN-Learn, which provides a comprehensive suite of functions for learning, inference, and visualization of BNs. BN-Learn supports various algorithms for structure learning, enabling users to discover the underlying network from data. For example, in a financial context, a bank might use BN-Learn to identify the relationships between different economic indicators and credit risk. By understanding these dependencies, the bank can develop more accurate risk assessment models and improve its decision-making processes. The flexibility of Bayesian networks also extends to their integration with other decision-making frameworks. For instance, BNs can be combined with decision trees to create influence diagrams, which represent both probabilistic and deterministic relationships. Influence diagrams are particularly useful in complex decision-making scenarios where multiple objectives and constraints need to be considered simultaneously. By integrating BNs with decision trees, professionals can evaluate different strategies and identify the optimal course of action under uncertainty. The practical application of Bayesian networks in decision-making is further demonstrated by their use in environmental management. Consider a scenario where policymakers need to assess the impact of different land use strategies on biodiversity. A BN can be constructed to model the relationships between land use, habitat quality, and species diversity. By inputting various land use scenarios, policymakers can predict their potential impact on biodiversity and make informed decisions that balance economic development with environmental conservation. Despite their versatility, The implementation of Bayesian networks requires careful consideration of certain challenges. One such challenge is the computational complexity associated with large networks, where the number of possible configurations can become overwhelming. Advances in computational techniques, such as Markov chain Monte Carlo methods, have addressed some of these challenges by providing efficient algorithms for approximate inference. These methods allow professionals to work with complex BNs without sacrificing accuracy, enabling the practical application of these models in real-world decision-making. Another challenge is the elicitation of probabilities from experts, which can be subjective and prone to bias. To mitigate this, structured elicitation techniques, such as the Delphi method, can be used to gather and refine expert opinions. By combining insights from multiple experts and iteratively refining their judgments, professionals can develop more robust probability estimates for their BNs. This collaborative approach ensures that the network reflects a consensus view, enhancing its reliability and credibility in decision-making contexts. Bayesian networks also offer a robust framework for sensitivity analysis, which assesses how changes in input variables affect the output of the model. Sensitivity analysis is crucial in decision-making as it identifies the most influential factors and uncertainties, allowing professionals to focus their efforts on areas that have the greatest impact on outcomes. Tools like Netica and BNLearn provide built-in functions for conducting sensitivity analysis, enabling users to systematically explore the effects of different assumptions and data on their decisions. The effectiveness of Bayesian networks in decision-making is further supported by empirical evidence. Studies have shown that BNs can lead to more accurate predictions and better decision outcomes compared to traditional methods. For example, a study in the field of medicine found that BNs outperformed logistic regression models in predicting patient outcomes, demonstrating their superior ability to handle complex dependencies and interactions among variables. In conclusion, Bayesian networks are invaluable tools for decision-making, offering a structured and flexible approach to reasoning under uncertainty. By providing a graphical representation of dependencies among variables, BNs facilitate the analysis of complex systems and enable professionals to make informed decisions based on both empirical data and expert knowledge. Practical tools like Netica and BNLearn make it feasible to implement BNs in various domains, from healthcare and finance to environmental management and engineering. Despite challenges such as computational complexity and subjective probability elicitation, advances in algorithms and structured elicitation techniques have enhanced the applicability of BNs in real-world scenarios. Through sensitivity analysis and integration with other decision-making frameworks, Bayesian networks empower professionals to navigate uncertainty and optimize their decision-making processes, ultimately leading to more effective and strategic outcomes.